We've spent the last couple videos analyzing what a confidence interval is, and now we're actually going to construct a confidence interval. So our learning targets today, we're going to check the random and large counts conditions for constructing a confidence interval for a population, and today we're focusing on proportions. We're going to determine the critical value for calculating a confidence level of C percentage confidence interval for a population proportion using either table A or technology, and then we'll calculate a C percentage confidence interval for a population proportion as well. So you guys have been flipping bottles for the past few years. Now we're flipping Hershey Kisses, and we want to see. We know that when we toss it, sometimes it lands flat, sometimes it's on its side. What proportion of tosses will land flat? So if we were in class and I actually bought you guys Hershey Kisses, you'd have 50 of them, or you'd toss one 50 times or some combination thereof and calculate the proportion that land flat. When I did this, I got that 16 landed flat. So we will say that, let me get this a little larger for y'all. So when I did this, I saw that 16 landed flat out of 50. So that gives me 0.32 is my proportion. And this is my point estimate, and I want to call it P hat. So let's identify population, parameter, sample, and statistic here, just like we have been doing the last couple of units. So the population is going to be all Hershey Kisses. And our sample is the 50 that we flip. And we would randomly select these by purchasing them at a store. And maybe if we have a lot of them, you'd randomly select 50 of them. Our parameter, the thing we're trying to estimate here, is P. That is the true proportion of kisses that land flat. And the statistic, the P hat that we created, is going to be what we just found right before, everything right here. So 16 out of 50, that's what we found above. And we want to make sure that is P hat. So P is our true proportion, P hat is our sample statistic that we got from flipping 50 of them. So you can do this on your own, and you might have some different values here, or you can just jot these numbers down. Next, we're going to build on what we did last unit in 6.4. We're going to calculate the standard deviation and sampling distribution of P hat. So let's write down this equation real quick. So we want our standard deviation. Let's try and make this a little larger. Our standard deviation of P hat, so we want a little subscript P. We want to get back out of that, is going to equal. We want the square root of, and then P hat times 1 minus P hat, all divided by, so we got to highlight everything underneath the square root, and divided by N. So let me get rid of this one and move this up and over a little bit. Remember, these are a little trickier to move on Cami. And we want to add in our hats to our P's because we don't have a true proportion P right now. So we are estimating our standard deviation using our sample statistic of P hat, the 16 out of 50. So let's plug in the values that we know. We know all of these values. So we need, again, the square root bar. Please give me the square root bar. Thank you. And we're going to use our P hat that we created from our sample of 16, which is 0.32, times 1 minus 0.32, which seems like 68%. And all that divided by N, our sample size was 50 kisses that we flipped. And then we can type that into our calculator. and get about 0.066. Kind of round it a little bit. So we have our standard deviation, we have our p hat now. A couple important questions before we can take a confidence interval is randomness. First, was the sample a random sample? Yeah, we randomly selected all of this from wherever we get our Hershey Kisses. So yes, we randomly chose 50 kisses. So the reason we want this randomness is that the sample should be representative of the population. And we want that so that we can generalize our conclusions to all Hershey's Kisses. Make that a little smaller for y'all. Should be better. So we want to make sure that we have randomness here so that we can generalize our conclusions from the sample to the population. So we do have a randomness condition that we have to make sure we consider that we have randomness. Next, would it be appropriate to use a normal distribution? So we talked about this again last unit in 6.4. We are going to use our large counts condition. And so we want to make sure that n times p hat, let's get our equation editor, n times p hat is greater than or equal to 10. And we want to make sure that n times 1 minus p hat is also greater than or equal to 10. So let's check. When I plug in these values, I'm just going to copy hopefully that. So I have n is 50, my sample size is 50 times 0.32. That gives us 50 times 0.32 gives us 16, which is indeed greater than or equal to 10. And then when we do the opposite of that, we have 50 times 1 minus 0.32. That will give us 34, which is also greater than or equal to 10. So yes, it would be appropriate, and we know because of this large counts that we have checked. So we need to check and see that n times p is greater than or equal to 10, n times 1 minus p. And in this case, again, just like before, we need to use p hat because we do not actually have a true proportion yet. So next, in a normal distribution, we know from first semester talking about our normal distribution and our rule R67, 95, 99.7, that 95% of the data lies within approximately 2 standard deviations of the mean. So we can say with confidence that about 95% of the data lies within 2 standard deviations of the mean. And when we practiced, estimating our margin of errors last class, this was one of the things that was suggested was 2 times the standard deviation of our sampling distribution. In this case, we're talking about our p hat here, our sample proportion. So we're calculating our margin of error, as it says right here. And in this case, we're going to do 2 times the standard deviation. So we have our estimated standard deviation right here of 0.066, and we're going to multiply that by 2. So let's show that work here. So that'll be 2 times 0.066. I'm going to go back and multiply by the exact value there, and we get approximately 0.132. That's our margin of error. When we move on, we're going to actually use the exact critical values instead of just 2. And we're going to get those from our table A, and we'll look at that in a little bit here. Bell means I need to hurry up. Find the confidence interval using the point estimate plus or minus the margin of error. So our point estimate is our sample proportion that we got, the 0.32, and we're going to add and subtract this 0.132. So we're going to have two values here where we're going to add and subtract that. So we want to see that 0.32. We want to add and subtract 0.132. So when I add it, actually when I subtract it, 0.32 minus the 0.132, I get 0.188. And when I add it, I get 0.452. So that is my confidence interval. And I can say that I am 95% confident, or we are 95% confident that the true proportion of kisses landing flat is captured in the interval 0.188 to 0.452. And if we're thinking about that as percentages, oh no. If we're thinking about that as percentages, then that would be like 19% to 45% or so. So let's jot all this down and wrap up our learning targets in the important ideas from the text. And this is estimating a proportion again. We'll do estimating a mean on a later video. So we need to check the large counts condition and the random condition. So we need to check. We need to check that it's random because it must be a random sample. So we can generalize the population. And we need large counts as well. And we can just go copy the large counts from here. We're probably gonna have to make all, ooh, that looked ugly. That looked ugly as well. Let's get an equation going down here. That's fine. And P is greater than or equal to 10, and we also want N times 1 minus P is greater than or equal to 10. I have to probably make some of this a little smaller. Move this in here for our large counts. Almost got it. I mentioned earlier that we were using 2 times the standard deviation, and that we'll have actual other values different than just 2 based on what our confidence level is. Our confidence level for 95% was close to 2. So let's look at our critical values is what they're called. And that's going to be Z, little asterisk is our critical value. So we get them from our Z table. So for 90%, our critical Z value is 1.645. For 95%, I believe someone in my virtual class came up with this value, 1.96. And then for 99%, these are the common ones that we'll be using. Our critical Z value will be 2.576. And so where do we use this in our formula here? So our confidence interval formula for our proportions is going to be the point estimate plus or minus the margin of error. And so our point estimate in this case is going to be p hat. And I want an equation over here because I'm going to have some students coming in real soon, so I got to go quickly here. So our point estimate here in this case is our p hat. I'll throw the hat on in a second. And then we're going to add and subtract plus or minus our margin of error, which is going to be that critical z-score. Can't get a little asterisk in. I'll put a little asterisk in here in a second. Our critical z-score times the square root, and this is just basically the standard deviation formula that we did earlier. 1 minus p, that whole thing, divided by n. I am creating a video. So we need to add in our p hat, our critical z asterisk, our p hats. Hang on. And then we will practice this in class on application 7.3.